So we're going to talk about the binomial experiment. Bi means two. So a binomial probability experiment satisfies the following conditions. Number one, the experiment has a fixed number of trials. Okay, we call that fixed number n. So there's n trials. So like maybe n could equal 5. So we flip a coin 5 times. Okay, so each trial is independent and identical, meaning the probability is exactly the same every trial. Flipping a coin, I have a 50% chance of getting a heads every time that I flip that coin. Number two, there are only two possible outcomes of interest. For each trial. Now, those outcomes are either a success, represented by S, or failure, represented by F. Okay? So the probability of a success is equal to the letter P. The probability of a failure is the complement of P, which is 1 minus P, and that letter used is Q. This is equal to Q. Okay? So if I had like a 30% chance of success, then 1 minus 30%, that's a 70% chance of failure. That's the idea there when using the complement rule. Number three, the probability of a success is the same for each trial. It's always, the probability of success is always equal to P, no matter how many times that you do the trial. The success is always the same. The last criteria, the last condition, is the random variable. Remember, abbreviate random variable RV. X counts the number of successful trials. Okay, successful trials. Now, X could be equal to 0, could be equal to 1, could be equal to 2, all the way up to n. Because there's n total trials, you can't have more than n successes. So if n was equal to 5, then the most successes you could have would be 5. All right? So when I think of a binomial experiment, I think of it's used to model the number of successes X out of n consecutive, meaning one right after the other, independent, identical, Bernoulli trials with a probability of success equal to P. Okay? That is what the binomial distribution does. It's a model used to or model that the number of successes x out of n consecutive, one right after the other, independent, meaning one does not affect the next, identical, meaning each probability is the same every time, Bernoulli, either it's one of two outcomes, trials, with a probability of success equal to p. Okay? So we're going to do an example where we determine if it's a binomial experiment. It meets the 4 criteria. And if so, I want to find MPQ and list all the possible values of the random variable. First one, we have a procedure where there's a 70% chance of success. The doctor performs the procedure 6 times, and the X represents the number of successful surgeries. So, number 1, is there a fixed number of trials? Yes, there is. Fixed number of procedures. N equal to 6. There's 6 trials. Number 2, there are only 2 possible outcomes, either a success or failure. So there's a 70% chance for success and a 30% chance for failure. You're either a failure or you're a success. That's it. Only 2 outcomes. Number 3, the probability of success is the same every time. The probability of success is 0.7, 70% every time. And the last one, the random variable, counts the number of successes. Okay? The successful surgeries. Therefore, this is without a doubt a binomial distribution where n is equal to 6. The probability of success p is 70%. And the failure is equal to 1 minus p, which is 30%. Okay? With the next one, we have a jar. So in our little jar here, right, it's like a cross section of the jar. I've got 5 red marbles, 1, 2, 3, 4, 5. 6 blue marbles, 1, 2, 3, 4, 5, 6. And 4 green marbles, 1, 2, 3, 4. All right. Now you randomly select 3 marbles. Okay. So you randomly select 3 marbles without replacement, meaning when you pick up a marble, you don't put it back in, you pull it out. Okay. Let X be the number of red marbles. All right, so X can either be 0, 1, 2, or 3. You randomly select 3 marbles from the jar. Now, there's n equal to 3. It's fixed, right? That's good. Probability of success is you either get a red marble or you don't get a red marble. So red is one outcome. Not red is the other outcome. Okay, so that's good. Is the probability of success the same for each trial? Let's see, what's the probability of drawing that first red out? Okay, well, how many reds are there total? Let's think about this for a second. How many reds are there total? Well, there's 1, 2, 3, 4, 5. So the probability of that first red is equal to 5 out of how many total? 5, and then 10 gets me 15. So that's 1/3, right, for that first red. Now say I pulled the red out. It's no longer in the bag. What's the probability of that second red? Well, there's only 4 red marbles, but then I pulled out one of the marbles, so there's only 14 left. This is not equal to 1/3. 4 out of 14 versus 1 divided by 3, the probability changes. So This is like 0.29, and this is like 0.33. Now, it doesn't change much, but it does change. And since it changed, okay, it changed, that means that these trials are not independent. Therefore, it's not a binomial distribution, okay? Now, there is a caveat here, all right, and it's a nuance. And so here's the exception to this rule. For a random sample collected without replacement, that's what we're doing. We pull a marble out and we don't put it back. The events are dependent always, right? However, if we sample 5% or less of the population, then we can treat it as a binomial experiment. Okay? So we can treat it as a binomial experiment if we sample 5% or less. So what is that? That's little n, the sample, is less than or equal to 5% of the real population. Now, why didn't it work here? Well, what were we doing? We were sampling 3 out of the total 15 marbles, right? So our sample was 3 out of 15, which is 20% of the population, okay? But let's change the game here. Instead of having 5 red marbles, say you had 500 red marbles. Say you had 600 blue marbles, and say you had 400 green marbles. That's a lot bigger bag, right? So say you had a bag and you had 500 reds, 600 blues, and 400 green. And now you were going to get 3 marbles out. All right, so if you take 3 marbles out of this, well, let's think about it, okay? So how many marbles are there total? Instead of 15, there's actually 1,500, okay? 1,500 total. So the probability of drawing the first red is equal to what? It's equal to 500 out of 1,500, which is still 1/3. But the probability of drawing that second red is equal to 499, because I took 1 red out, over 1,499, okay? Now, 499 divided by 1,499 is 3328. So approximately 0.3328, whereas this is approximately 3333, right? So if you look at this, you see that those values are extremely close to one another, okay? Close enough so that even though they are technically different probabilities and technically don't satisfy the binomial experiment, we can actually pretend like it is a binomial experiment because it's 5% or less of the population. How do I know it's 5% or less? Well, 3 marbles out of the 1,500, what percent is that? 3 out of 1,500 is 0.002. So that's 0.002, which is equal to 0.2%. That's certainly less than 5%, okay? So that's the idea. As long as the amount that we're taking out of the pot, or whatever jar or whatever that we're drawing from, is less than or equal to 5% of the total population, then we can pretend that it's a binomial experiment. Otherwise, anytime we draw without replacement, those are dependent events which change the probability on each draw. Okay, so little nuance there, but just stressing that so you can kind of really get down in the nitty gritty of the probability of success is the same for each trial.